Hello, I'm Siddharaj Bhatta, and in this video I'll talk about the empirical rule, and Chebyshev's theorem. So this is my email address. Let us first talk about the empirical rule. The empirical rule applies to the bell-shaped data, that is normally distributed variable. It says that in a bell-shaped data, about 68% of the observation lies within one standard deviation away from mean. That is, mean plus minus one standard deviation. This range includes almost 68% of the observation. This also implies that the probability that any observation will lie within this range is 68%. Next, about 95% of the observation lie within two standard deviation away from mean. So what it shows that x bar plus minus 2 standard deviation, this range includes 95% of the observation, or in other terms, the probability that any observation will lie within this range is 95%. And lastly, almost all observations lie within 3 standard deviation away from mean. Sorry for the typo. 3 standard deviation away from the mean. So it shows that the range x plus minus 3 standard deviation, it covers almost all of the observation. It's 99.7%, which is almost all. So, or in other words, it becomes almost certain that any observation selected or any observation will lie within this range. We can explain it through a graph. So in this graph, this range is, the striped range is the range for mu plus minus 1 standard deviation. The striped range is mu plus minus 1 standard deviation range. So almost 68% observation lie here. So the yellow painted range is the range for mu or mean plus minus 2 standard deviation, and almost 95% of the observation lie here. And this whole range from here to here is the mu plus minus 3 standard deviation, and almost all area is covered by this range. This means almost all observation will lie in this range. So this is the empirical rule. Now next, let us go to the Chebyshev's theorem. So Chebyshev's theorem is different from the empirical rule in the sense that it can be applied to any types of distribution, whereas the empirical rule applies to the bell-shaped data only. So according to this theorem, if we take a certain standard deviation interval from the mean, at least 1 minus 1 over k square of the observation lie within that range. So two things are important here. The first thing is the value of k is greater than 1. Value of greater than 1 means we can talk about the range mean plus minus 2 standard deviation, 3 standard deviation, and so on. But we cannot derive how much of the observation lie within 1 standard deviation, because if we put k equals to 1, it is almost 0. So now, for example, we take k equals to 2, then 1 minus 1 over k squared equals to 75%. So it shows that at least 75% of the data lie within mean plus minus 2 standard deviation. When k equals to 3, 1 minus 1 over k squared is 88.9%, and we can say that at least 88.9% of the data lie within mean plus minus 3 standard deviation. It can also be explained with the help of a graph. So this range is mean plus minus 2 standard deviation, and this range is mean plus minus 3 standard deviation. So at least 75% of the observation is covered by mean plus minus 2 standard deviation, and at least 88.9% of the observation is covered by with this mean plus minus 3 standard deviation range. So to provide a proof of this Chebyshev's theorem, we consider the formula for sample variance as s squared equals to 1 over n minus 1 summation xi minus x bar whole square. And we consider a range mean plus minus k standard deviation. So if we consider a range, this is mean minus k standard deviation, this is mean plus k standard deviation. So this is mean value. So now we divide our total n observation into two parts. One part lies inside the range and the rest of the observation lie outside. So inside there are n1 observation, outside there are n2 observations, so that n1 plus n2 equals to n. Now with respect to this, we decompose the variance formula in this way. So inside n1 observation, outside n2 observation, and the total n observation. Now we have to show that the percentage of observation lying inside the range, that is n1 over n. n1 is the observation inside the range and n is total observation. So this is the percentage of observation lying inside the range is greater than or equal to 1 minus 1 over k squared. So this is the statement to be proved. Now let us decompose the formula for variance in this way. So this is our range, this is x bar, this is k standard deviation, this distance is k standard deviation. So now if we take any observation outside xi, the difference between these two terms is greater than k standard deviation. So the main feature of this one is xi minus x bar is greater than ks, because it lies outside the range. So now we divide the formulas for sample variances. S squared equals to 1 over n minus 1 same. So we divide this into two parts, one for inside and another for outside. So this is for inside. This is xi minus x bar square. So this is for inside the range, and there are n1 observations, plus xi minus x bar square, and this is for outside the range, and there are n2 observations. So now we take this part. And we start from this statement. For outside the range, what is true is that absolute value of xi minus x bar is greater than ks. So if we look at this graph, this becomes very much clear. If we take any observation outside this range, xi minus x bar is greater than this ks distance. If we take any xi here outside the range, xi minus x bar is greater than or equal to ks. So we start from this and we square both sides. When we square, this becomes xi minus x bar squared equals to, is greater than or equal to, so is greater than or equal to k square s square. So now we take summation. So this remains the same, greater than or equal to. So here we are adding constraint. So if we are adding 5, this becomes 5n. If we are adding a, this is a plus a plus a and a. We are adding a constraint k square s square, and this becomes n2 k square s square. It is because there are only n2 observation outside the range. So only n2 observation outside the range. This is summed over n2 observation only. So this becomes n2 k square s square. So now we take this relationship and substitute this in this formula. Substitute this. I mean, summation xi minus x bar square is greater than or equal to n2 k square s square. So we substitute here. So now when we substitute this expression for here, this equality sign changes because we are substitute a smaller number here. So this is greater than or equal to this number. So now instead of this expression, which is here also, where we are substituting a smaller number. So if we substitute a smaller number here, this sign changes into greater than or equal to. So now we write in this way, s square is greater than or equal to, s square is greater than or equal to 1 upon n minus 1. So this expression for inside the range remains the same, xi minus x bar whole square, this remains the same, plus n2 k square s square. Again, why this equal to sign has changed into greater than or equals to, it is because we have substituted this number here, and this number is smaller than this expression, which is this expression. So this has appeared to greater than or equal to. Now we do a little mathematical trick here. This is s square is greater than or equal to. So this is a positive number, this number is positive number. So we can assume it to be positive 1. So if we delete a positive number from here, so this left hand side is already greater than or equal to right hand side. Left hand side is always greater than or equal to right hand side. For example, 5 is already greater than or equals to 4 plus 1. Now if we delete a positive number from this side, the inequality sign does not change. This means we can delete this number, this positive number from here without affecting the inequality sign. So now this becomes s squared is greater than or equal to 1 upon n minus 1 n2 k square s square. Now this is s squared is greater than or equal to 1 over n minus 1. So we do another mathematical trick here. So this becomes n minus n1 k square s square. Because n1 plus n2 equals to n implies n2 equals to n minus n1. Now s square is greater than or equal to, so this is n over n minus 1 minus n1 over n minus 1 times k square s square. So since s square is a positive number, this can be cancelled from both sides without inverting our inequality sign. So now this becomes this becomes 1 is greater than or equal to n over n minus n1 over n. K square. So again we have done a simple mathematical trick here, that is this expression is equal to n minus n1 over n. Previously it was n minus n1 over n minus 1. So to simplify this is n2 over n minus 1. So we were dividing by n minus 1, we were dividing by a larger number, we were dividing by a smaller number, and we ignored minus 1, negative 1, and now we are dividing by a larger number. We are dividing by a larger number. So if we divide by a larger number here, its value will further diminish. I mean n over n minus 1, this is greater than this, and this term is greater than this. This is 1, this is greater than 1. This is n1 minus 1, this is greater than that value. So what we did here is we replaced n minus 1 by n, and we replaced the denominator by a larger number. So if we replace the denominator by a larger number, its value will further diminish. And less this sign, nothing happens to this sign. This sign is still retained. Means we can safely do this. So we can take an example of this. For example, 2 is greater than 1 over 4 minus 1 over 5. Now what we can do is we can increase the number by 1. 2, 1 over 5 minus 1 over 6. Here 1 over 5 is smaller than this, 1 over 6 is smaller than this, so nothing happens to this greater than sign. So we have done the same thing here. Now this simplifies to 1 is greater than or equal to 1 minus n1 upon n times k square. Sorry, one bracket has been missed here. So this becomes 1 is greater than or equal to k square. Sorry, this k square can be taken here. 1 upon k squared is greater than or equal to 1 minus n1 over n. Now finally n1 over n, n1 over n, we take this side, is greater than or equal to 1 minus 1 over k squared. So this is the result. So this is the percentage of observation lying within the range, which should be at least 1 minus 1 over k squared. So thank you for watching this video and subscribe to my channel.